is a so-called inner product. An inner product. Inner product. An inner product now is, I'm going to define the, I don't know what notation you use, but the notation that textbook in the US use often is you take a vector U and inner product with a vector V. So take two vectors and give you another number. Okay. So that is the inner product. And if you this number here can be either this number can give you a number either real numbers if you have defined this thing here is a real, or a complex number if this thing here is a complex. Okay. So let me make it. So this is the inner product here, and let me give right away now an example of that. So an example, for example, if I have thing in the vector space Rn. Okay, so I have an n-dimensional Euclidean vector space. Right? Each signal have n samples. Okay, and n real number. So I have two signals, and I want to take an inner product between these two signals. So the signal U times V here, this thing here can be defined in the summations n go from 1 to n. No, I have a dimension here, so we take the index I go from 1 to n of U I V I. Okay. So I take two vectors and I take the inner product. Okay? So that's very familiar inner product, right? The cross products, the dot product. Okay? So that inner product. And this summation here, if I started to use a vector now, I can write the vector now, a signal vector now. Typically, we write the column vector. A column vector. So in a column vector, you have single hits, and in the column vectors, so it would be equal to hit 1, hits 2, to hits n. Okay. So an n-dimensional Euclidean vector space, any one of those vectors. I have n and these. Okay. And to define our inner product, simply take this summation and take the sum, and so I take the product and I take the sum. Okay. And I can write the more compact form is simply I take one vector with the transpose and multiply with another vector. Okay, so I can write this now here is U transpose times V. Alright, is that something okay with you? I take the vector U transpose and multiply with this. So I'm going to use, you can see a little bit confusing here. I have U here as the whole vector, and V here as a vector, and I can write this together. Okay. So that is in a real form. Now sometimes the signal we use, especially useful for the Fourier transform, we would use the complex number. Right? Complex number, then the inner product of the complex number defined slightly different, and I take the same thing, summation I from 1 to n U I V I, but now I have to take the complex conjugate of one thing. And in this notation, let me take the complex conjugate of the first one. You have to define them a little bit carefully, just follow one notation there. Okay, so take complex conjugate in one, and then that allows me to write it. Now U is I take U and I transpose it, but then I take the omission. I take the conjugate of each number. Anyone understand the complex conjugate? What is complex conjugate in Vietnamese? Linear foot. Okay, linear foot. Okay. And the name of Okay, this is the transpose, and this one here is the H here stands for the Hermitian. So have X here, and somehow we can define X transpose. Okay. So X transpose is equal to the vector here, x1 complex conjugate, xn complex conjugate. So you see that I need this, right? And this is, if you say them in English, we would call X Hermitian. That operation. Right, so these are two specific examples of two vector space that I have an inner product. We can have other one, right? Other vector space. More general, we can define more general inner product. So we have to understand now, what is inner product telling us? Right? What is the inner product? The inner product allows to do something. Maybe we start with the simple two-dimensional Euclideans. So if I have two inner products, vector space, I take an example here. I take an inner product of we want to have those simple vector. I'm going to have some special signal. Before we have the delta n, but now in the inner product vector space, I'm going to use a vector E. I have trouble now because we are okay. So the vector now you know like the whole thing here. So the E here, let's say I have E on here. E is the vector space, the vector, especially is have 0, 0 everywhere and have 1 at the I. Okay, so that is like the delta n minus I signal. Okay, this is the basic signal. So I have this, so that is a basic vector. And what happens with this signal? If I take an inner product, so for example I take this E1 here and have a signal X here. So if I take X and inner product with EI here, what does it give you? It gives me Xi, right? It gives me the Xi now. It just gives me the component I of the vector X. Okay. So that gives me something like, okay, in taking that inner product, and we see later on something quite important happen for not just the simple signal, but any other transform can be interpreted this way. Okay, so that tells me, and the bigger the Xi, small Xi here, that means the more strong component EI in this Xi, right? Small signal. For example, so the inner product is quite remarkable properties. Another example here, and maybe I can let you to think about this. You can show easily. If I have two general vector here, let me call them X and Y, and I know that the angle between X and Y as alpha. Then the inner product, this thing blown from this elementary geometry course, we take X and Y here, these two, normally it would be equal to the magnitude of this, multiplied with the magnitude of this, multiplied with the cosine of this angle. Right? That's something you see before. You can show that easily. Okay. So the magnitude of this is